Have you ever stopped to think about the hidden rules that make the world around us work the way it does? Today, we're diving deep into the quantum realm to uncover the secrets that make solids, well, solid. I mean, think about it. You do it every single day. You plug in your phone, those metal prongs let electricity flow right through, no problem. But the plastic case around it, it stops that electricity cold, which is pretty important for not getting a shock. They're both solids. They're both made of atoms. So what gives? Why are they so completely, fundamentally different? Well, the secret, it's not actually about the atoms themselves. It's about what their electrons are doing, their secret lives, especially when they all get packed together in a crowd. And understanding that story, a story that happens at the quantum level, is the key to, well, all of modern electronics. For the longest time, the huge variety we see in solids was just a total mystery. Scientists had okay-ish models for gases and liquids, but solids? They were a whole other beast, a real puzzle. Before the 20th century, physics just couldn't crack it. I mean, the old classical theories basically said that materials shouldn't have such wildly different electrical properties. And yet, a piece of copper can be over a billion billion, that's not a typo, a billion billion times more conductive than a piece of quartz. Why? The old physics had absolutely no answer. It took the bizarre new rules of quantum mechanics to finally figure it out. So, to find the answer, we have to zoom in, way, way in. We need to step into the strange world of the electron and see what happens when these tiny particles stop being lonely and start getting packed together in the perfect, repeating pattern of a crystal. Okay, so in a metal, for example, the atoms lock into this beautiful, repeating grid called a crystal lattice. And here's where it gets really interesting. The outermost electrons, what we call the valence electrons, they don't stay tied to their home atom anymore. They're set free. They basically form this free-floating sea, a kind of electron gas that just swishes through this fixed grid of positive ions they left behind. Now, here is the absolute key. This is not like a normal gas. These electrons are quantum particles, which means they have to play by a very strict rule called the Pauli exclusion principle. In simple terms, it means no two electrons can be in the exact same state. So they can't all just pile into the comfiest, lowest energy level. Nope, they're forced to stack up, filling higher and higher energy states, one after another. And this one little rule, it changes everything. This whole stacking process leads us to one of the most powerful and honestly beautiful ideas in all of physics, band theory. And the best way to get your head around it is with a pretty simple analogy: highways and roadblocks. So because all those atoms in the crystal are in that perfect repeating pattern, their individual electron energy levels start to sort of blur together. They merge, creating these wide highways of allowed energies. We call them energy bands. If an electron has an energy that falls within one of these bands, it's on a highway. It's free to move. Think of it like an open lane on the freeway where traffic can just flow. But, and this is so important, between these energy highways, there are roadblocks. These are forbidden energy zones we call energy gaps. An electron simply cannot exist with an energy level that's inside a gap. It's a fundamental quantum no-go zone. You can be on this highway, or you can be on the next one up, but you literally cannot exist in the ditch in between. And right here is where it all comes together. A material's entire electrical personality, whether it's a conductor, an insulator, whatever, is decided by the relationship between two specific bands. The last highway that's totally filled up with electrons is called the valence band. The next empty highway just above it is the conduction band. And that space between them, that's the all-important energy gap. The relationship between these three things is the answer to our entire mystery. Okay, so we've got our model, our energy highways, and our roadblocks. Now let's put it to work and see how this brilliantly explains why materials behave so differently. Let's solve this thing.
Okay, just look at the difference here. On the left, you've got a conductor, like our metal plug. Its last filled highway, the valence band, is only partially full, or it might even overlap with the empty conduction band. This means electrons have tons of empty spots right next to them to move into. The tiniest little nudge from an electric field gets them flowing. But look at the right. For insulators in semiconductors, the valence band is completely full. It's a traffic jam. For an electron to go anywhere, it has to make a huge energy jump across that gap to get to the empty highway above. And this chart just makes it crystal clear. The size of that gap is everything. For a conductor, the gap is basically zero. Easy. But now look at silicon, a semiconductor.
The gap is small, about 1.1 electron volts. That's a tiny bit of energy. It's a jump, sure, but it's a manageable one. Then you have diamond, a classic insulator. The gap is enormous, a whopping 7 electron volts. It is almost impossible for a normal electron to make that leap. And that's why diamond doesn't conduct electricity. So here it is, the whole code, unlocked. Conductors, they've got partially filled bands, no energy gap, electrons flow easy. Insulators, they've got a totally full valence band and a huge gap, making flow nearly impossible. And then you have semiconductors, the really interesting middle ground, a full valence band but a small, crossable gap. And that special in-between property is exactly what we've learned to exploit. So if semiconductors are in this weird middle ground, how do we make them useful for, computers and phones? Well, the answer is a kind of quantum engineering. We found a way to deliberately hack this system to control exactly how conductive we want it to be. This incredibly clever hack is called doping. What we do is take an ultra-pure crystal like silicon, and then we intentionally sprinkle in a tiny, tiny but precisely controlled amount of a different element. We're adding an impurity on purpose. It's like adding one secret ingredient to a recipe that completely changes how it turns out. Let me show you how it works. A silicon atom has 4 outer electrons to make bonds with its neighbors. Now, say we swap one of those silicons with an arsenic atom. Arsenic has 5 outer electrons, so 4 of them form the same bonds as before, but now there's 1 electron left over. This extra electron is very loosely attached, and what it does is create its own little energy stepping stone right below the main conduction band highway. So now, it's incredibly easy for this electron to just hop up into the conduction band and start carrying a current. We call this N-type doping, N for the extra negative charge carriers, the electrons we've added. But get this, we can do the exact opposite. If we add an atom like gallium, which only has 3 outer electrons, it creates a vacancy in the crystal's bonds, a hole where an electron should be. This hole acts just like a positive charge. A nearby electron can easily jump into the hole, but when it does, it leaves a new hole behind. So it looks like the positive hole is moving through the material. This is P-type doping for these mobile positive charge carriers. And this is the punchline. This is the whole shebang. By combining these 2 types of doped materials, N-type and P-type, right next to each other, we can build junctions that control the flow of electricity with unbelievable precision. This is the fundamental principle behind the transistor, and therefore, it's the foundation of every single microchip in your phone, your computer, our entire digital world. This quote from Felix Bloch, one of the pioneers of this theory, just perfectly captures the magic of that discovery. He realized the electron wasn't some little ball bouncing off atoms like a pinball. It was a wave that could just glide through that perfect crystal pattern almost without any resistance. You can just feel the scientific delight in that moment, a moment that absolutely changed the world. So we started with a simple question about a phone charger, and it took us on this incredible journey deep into the quantum world to find the answer in these energy bands and gaps. But what's so amazing is that this theory doesn't just explain the world we see, it gives us the blueprint to engineer it. And as our ability to build things atom by atom gets better and better, the real question is, what new quantum secrets are we about to unlock next?